Here in Chapter 4, we are going to be talking about critical thinking and scientific reasoning. And really what we're going to be talking about here are some research methods issues, which may sound a little bit dry and boring, but the reality is that the way that we consume information is very important, as you learned back in Chapter 3. So we'll talk a little bit about research methods, some of the pros and cons, some of the ways that we can make mistakes when we are choosing a research method protocol, etc., etc. This will help set you up really nicely for the research methods class as long as you have a good understanding of this stuff. So what we're going to try to do in this chapter is explain how non-scientific and scientific reasoning differ. We're going to talk about strengths and weaknesses of the various methods. We are going to determine whether a cause and effect relationship is likely to exist based on the way that you choose to explore a question. We're going to talk about the limits of the scientific approach and some inductive reasoning, and then recognize those thinking errors. We tend to do that in each chapter, where we find out something new about critical thinking and the way that it leads to errors in the way that we think. So we start out with what do you think type of question, just kind of a rhetorical thing to think about. And we'll talk about the Heaven's Gate cult, which is interesting because this is something that I remember pretty vividly. The Hale-Bopp comet back in 1997 was an interesting thing. It made a very close approach to Earth, as far as celestial bodies go. It was close. And there was a group of people that believed that if they were to kill themselves by suicide, then the aliens that were hiding in the tail of that comet would open up the gates to heaven and they'd be able to be saved from the wrath. Okay. So that's what they believed. And I think it was 37 people died in that. And it was because they voluntarily drank something and it killed them. Usually when you have cyanide, it's not a good thing. So what do you think? When people join a cult, do they endorse all of the cult's beliefs or lose their ability to think critically? And lose their ability to think critically. Okay, so what do you think about that? Do they lose all of their beliefs? And then you have to think about, well, wait a second, what is a cult? What would constitute a cult? Does it mean that I join a group and we believe the same thing, or does it have to be nefarious? What's going on with the cult? Does observing media depictions of aggressive behavior cause a person to behave aggressively towards someone else? And how would you go about answering that question? You can have your own thoughts and opinions, you can make observations, but how do you answer that question in a scientific way? So again, this is the difference between scientific and non-scientific reasoning. Does raising self-esteem improve academic performance? Is there a link there? And is it a causal link or is it a correlative link, meaning correlation? And can science answer all questions? Very interesting thing. We talk a lot about how the scientific method is the standard for answering questions, but can it answer all questions? And I'll even push it a little bit further. Should it be able to answer all questions? Okay. So let's take a look at comparing scientific and non-scientific approaches. So something that we know about science and an approach to critical thinking is that science is empirical, meaning that we need to observe something. If you've seen the TV show or any of the movies called Jackass, then you see that there is a lot of empirical evidence for the types of things that they have questions about. Mostly, do things hurt? Are things embarrassing? Those kinds of things. But they do the things that they want to do in order to answer the question. So there's a kind of an empirical approach there, as opposed to talking about, hypothetically, would it be funny or would it be painful? So they go through the observations and they verify their suspicions about pain and embarrassment, etc., etc. Okay. And when we make these empirical observations, we're using those observations to get a more objective approach to what we witness in the world. It's not enough that we think that people think a certain way or that people don't like cafeteria food. We have to actually ask those questions. We have to seek those out. It's not enough that we think that a medication works on a particular illness. We need to actually measure that. We need to figure out a way to measure some kind of baseline illness, and then we need to measure that illness again after the drug had been introduced. But we also have to rule out other things. So we'll talk about the three necessary qualities of cause and effect relationships a little bit later in this lecture. Okay. Science has built-in checks on the quality of data, which helps science to be self-correcting. So we'll talk about hypothesis testing. And the way that we form a hypothesis can help us to answer questions in a meaningful way, and helps us to have what are called falsifiable hypotheses, meaning that we have to have a hypothesis that's worded in a way that we can correct ourselves or learn more information if we are wrong. Okay. And then kind of the gold standard of the method of science is that we use high quality research studies, usually experimental designs and other quantitative designs are helpful in specifically answering questions, but we also have qualitative approaches. Again, we'll just gloss over the approaches in this class because we have an entire class, research methods, dedicated to it. So we have science that we need to think of as an approach to knowledge and evidence. So again, it's using those aforementioned methods of science in order to answer questions. So scientific approach to inquiry. So how do we ask questions? How do we wonder? How do we explore the questions that we have? Okay. So science wants to seek a lawful relationship between variables based on observable data. Lawful is an interesting word there. Lawful really means, is it verifiable? Is it reasonable? Is it sensible? Okay, not just what do you think or what did you witness, but what's the preponderance of evidence saying about a particular relationship between a variable like aggression and watching violent TV shows and things like that. Okay. So we want to see if there's a relationship there, not just based on what you think. Okay. A variable is something that we have to keep in mind. A variable is a characteristic that can take on different values, which is kind of like a textbook definition. A variable can be a question like, what's your shoe size? That's a reasonable variable. It could be some kind of information you're getting from somebody, like about sex and gender, or it could be, how do you feel on a scale of 1 to 10? How many times have you gone out to eat this week? A variable can be anything that has particular values. Okay. And the relationship between two variables occurs, and this is really focusing on a specific type, and I wish the book wouldn't be so specific in this example, but we can go along with it. A relationship between two variables occurs when the score on one variable changes consistently with scores on the other variable. So if we want to talk about a variable like shoe size and a variable like age, up to the age 18 or so, your shoe size will go up at about the same rate that your age does. There will be some kind of relationship there. The other thing that can happen is that you can see that maybe there is a difference in test scores between freshmen and seniors. So if you have a variable called test score and then a variable called class standing, you would have two groups of people. You would have freshmen and seniors, and you'd look at all their test scores and see if there is a difference between them based on whether or not they're freshmen and seniors. So the variables that we use are really identifying the questions that we have about a particular research study. So for example, in the last one I just mentioned about the test scores in freshmen and seniors, you'd have a question that would be something like, is there a difference in these test scores based on whether or not people are freshmen or seniors, so first year versus last year? And then you'd come up with the variables, you come up with the tests that they would take, and then you would measure their level, their class standing, and then you'd be able to see if there's a difference in those variables. It's not a particularly difficult concept in the broad sense, but using them specifically can be a little bit tricky. Okay. What's nice is that even when we have variables that we're unsure of, we can do something called operationalizing them. We call these operational definitions. So when we have a variable like class standing, and I'm interested in a particular class standing, I could define or operationally define class standing as either freshmen or seniors. Or if I wanted to operationalize some kind of construct like happiness, I could say, okay, on a scale of 1 to 10, how happy are you today? That would be my operationalized definition for happiness. So I've given a kind of this rigid, objective way of measuring it. Now, it is based on self-report, so that there's a limit to objectivity there because people only report the way that they feel in that moment. But generally, it's a reasonably reliable way to ask people how they're feeling in that moment on a scale of 1 to 10. Okay. So the example that the book gives is that social psychologists that study helpfulness can use a self-report scale to measure participants on their helpfulness, on how helpful they think that they are. You might be thinking to yourself, well, can't people lie? And the answer is yes, people can and do lie, especially on a question like how helpful are you, because people want to seem like they are amenable to the question, or there's some kind of character that they want to present. So people can and do fib on that. So that might lead to another question. Well, how do we measure something like helpfulness? People lie about it. Well, you could set up an experiment, which we'll talk about a little bit later, or some other way of objectively measuring whether or not somebody is helpful. Now, when we operationalize a variable, we are defining it in a particular way. Okay, so what that means is that the researcher gets to choose within reason how to define a variable. If you wanted to define happiness on a scale of 1 to 10, you could do that. If somebody else wanted to define happiness on a scale of -10 to +10, where 0 was a neutral thing, you could do that as well. If somebody wanted to operationalize happiness as the number of times somebody smiles during a 5-minute conversation, they could operationalize it that way too. There are different ways to operationalize a variable, but some of them are more reasonable than others, especially depending on what you're trying to measure. Now, when we have, when we're looking at a scientific inquiry and we're trying to answer questions scientifically, we need to develop hypotheses about the nature of the question that we are asking. So a hypothesis is a statement that predicts what might happen between two or more variables. Okay? So if we use the example from the book, based on social learning theory, a group of observing a helping model will engage in more helping behavior than a group not observing the helping model. Okay, so what happens there is that we think that if people see other people helping, then they themselves will help. If people don't see other people helping, they're less likely to help. Okay, that's kind of what happens here. If we wanted to make this a very tight hypothesis, you would say that people who are group 1 who watches other people helping will help more than group 2 that does not watch other people helping. And we'd get a little bit more specific. We'd put numbers on it and say that they would be likely to a 95% likelihood. So we'd probably base that on some kind of critical value or alpha level. But again, that's something that we'll talk about in stats and research methods more than in this class. But the hypothesis is what you expect to be, expect the relationship to be between the two variables. We won't get into it here, but there is also a further delineation from hypothesis called the null hypothesis and an alternative hypothesis, or also known as a research hypothesis. We're not going to get into that, but if you hear those words, know that they kind of go along with the hypothesis. So, hypotheses can predict relationships in two main ways. There are more breakdowns than what we're talking about here in terms of the way that we can observe a hypothesis, but generally a hypothesis will predict either that two variables are associated or that some variables or two variables will have causation. Okay, so there might be an association between variables like shoe size and height, or by how much self-esteem somebody has and what their test scores might be. Or there might be something about causation, like people who study the night before will have higher test scores. So you can have a group that studies and a group that does not study, and then you could measure their test scores, and you could, based on the findings, find that if people study the night before, then they have higher test scores. Again, it gets more specific than that, but generally that's what a hypothesis is looking to do. Either see if two variables are associated, or if you can see significant differences between groups in some measurement. Those are kind of the two main breakdowns. There are other ways again, but that's a very good broad definition for the way that hypotheses work. So if you want to predict an association, okay, that is, do two things move together? Do two variables move together? Usually you're measuring two numbers against each other, like on a scale of 1 to 10 of happiness and the amount of caffeine that you drink in the morning, right? Because some people need coffee to be happy. I don't drink coffee to be happy. I usually use soda, so I'm just as guilty. It's just a different form of caffeine. Leave me alone. This isn't about me. Some hypotheses make predictions about the association between variables. For example, when people feel more anxious, they smoke more cigarettes. Okay, so if we have a situation where, I'm going to fix that, it's kind of bugging me, should be a comma, not sure what happened there. When people feel more anxious, then they smoke more cigarettes. So we're measuring anxiety, presumably on a scale of like 1 to 10, where 1 is not anxious at all and 10 is incredibly anxious. And then the number of cigarettes that you smoke is measurable just in terms of quantifying the number, right? So when those two variables move together, so if we do indeed find an association, then we will ask a bunch of people how anxious they are and how many cigarettes they smoke, and then we'd be able to plot those on a scatter plot and find that, oh boy, as people are less anxious, they smoke less cigarettes in general, but as people are more anxious, they smoke more cigarettes. And if that is a trend that we see persisting, then we can say that those two variables co-vary, meaning that they move together. Okay. Now, what we have to understand here is that we are not looking at what's called causation. We can't say that when that anxiety is causing them to smoke more cigarettes. It could be a nicotine addiction that causes them to smoke more cigarettes, and they just have less willpower or whatever it is. Or maybe they have more money because cigarettes are expensive. So maybe it's not about anxiety, maybe it's about money. So we know that those two variables seem to co-vary, but we have to rule out other things like other explanations, et cetera, et cetera. So one of the mantras that we have in research is that correlation does not prove causation. Just because two variables seem to move together does not mean that there's a causation behind it. Now, there are cases where there probably is causation behind it. For example, the taller you are, the bigger your shoes are. Okay, some people might say, well, geez, that's kind of a matter of development, right? I said, yeah, that is a matter of development, and the human body grows in a certain way, and your feet grow to accommodate your height within a certain range. People who are really tall have really big feet. People who are short have really small feet. So in general, that is the trend. Your feet are made to grow bigger to accommodate how tall you are. It's a matter of physics. Your body's cool like that. It does that. So in that way, yeah, okay, fine. Shoe size probably is caused by how tall you are. And you'd probably think, well, geez, is how tall you are governed by your shoe size? Probably not. It's probably the correlation probably, or excuse me, the causative relationship probably goes from height down to shoe size, not the other way around. It'd be funny. Your body is kind of like, oh, I got to grow taller because we have big feet. That doesn't seem sensible. So causal predictions are based on having three major aspects in play that we're going to talk about later. But those two variables need to co-vary like we looked at in the last slide. There has to be what's called temporal precedence, meaning that one thing has to happen before another thing in order for it to cause it. And then you have to rule out other explanations for it. We'll talk about those a little bit more specifically later. But those are the three aspects that you need to have this causal prediction. Okay, so if you have a hypothesis that says that something like men will have higher test scores than women will. Okay, so you can have that, and maybe what you can suggest is that there is some kind of causation where men, because some kind of characteristics about men is true, they'll have higher test scores. Or maybe if we make it more biological, men will have higher testosterone because we know that hormonally that there is a difference between men and women in terms of testosterone. So that maybe the sex of the person, the biological sex of the person, governs the amount of testosterone. However, embryologically we know that hormones also will govern the sexual characteristics of the human too. So that could actually be a causal relationship in both directions. Very interesting. Anyways, what we recognize there is that there is some kind of timing there. Something happens before another. Okay. The example they get is that the book gives us about studying. So if people study more, it causes them to learn more than people who do not study as much. Okay, that kind of makes sense, right? So studying more causes you to learn more. I guess that makes sense. We probably know that there is a limit to that, right? Because you study too much, you start to, not be able to think straight. You're not processing things well, and it's actually inhibiting your studying. So there's probably some kind of curvilinear relationship, but that's never mind. Shouldn't have even mentioned that. These two variables are more than just associated because something is happening before another. So studying happened before the learning. Okay. If you take away the studying, you take away the learning. So there's covariation of cause and effect, and then you you have to rule out other things in order to make this a certainty. So are people getting like injected with some kind of serum that makes them learn? No. There's probably not another reasonable explanation for the relationship there. So we can say that one variable caused the other variable. So when we have a hypothesis, we have to make sure that the hypothesis is actually testable. And it might seem odd that, well, if we have a hypothesis, isn't it always testable? And the answer is no. Some people will ask questions that are theoretical. Some people will ask questions that are practically impossible to answer. Some people will ask hypotheses that ask to prove non-existence, right? So if you want to talk about, I'm here to prove that that the boogeyman does not exist. Okay, you really can't prove that it doesn't exist, right? Because you have to like figure out what the boogeyman is, and maybe it's a cultural thing, or maybe the boogeyman does exist, but nobody's ever seen him. So how would we know about him? So we have to think about how we test the non-existence of things. Normally, hypotheses are what are called positively framed, meaning that we ask positive questions or questions that talk about the presence of something or the association of something, not the non-association or the non-presence of something. Okay. So, one of the questions that kind of is a classic question about hypotheses and being testable is a question of how many angels can dance on the head of a pin. Okay, that's not testable, mostly because you have to define what an angel is. It has to be present. You have to be able to identify it. And angels are part of religious beliefs, so it's interesting to try to test that when not everybody has the same religious beliefs. So it's not a testable hypothesis, but we can test the question: how many people believe in angels? Okay, we can answer that because we can ask people about what their beliefs are. We can quantify the number of people that believe in angels as we have defined it in the question, and maybe we can say something like we can come up with a hypothesis that says something like people who believe in Christianity will believe in angels more than people that don't believe in Christianity, right? Because maybe an angel is a Christian construct in this case, and that angels don't exist in other religions or many other religions. So we have this question that we can now answer because we framed it in a way that we're talking about a belief and not about the actual presence of the thing, right? So again, we can answer questions as long as we can format them in testable ways. A tricky part of this is that our hypotheses need to be what are called falsifiable. And when you think about a falsifiable hypothesis, you might think, well, I don't want a falsifiable hypothesis because I want it to be right. Well, that's not exactly what falsifiable means. What it means is that we can have a hypothesis that can be disconfirmed. Okay, so what that means is that we ask a question that can be wrong, that can have a wrong answer, or that can have an answer that we don't expect. We can create a hypothesis where we suspect something to be true and it has a possibility of not being true. Those are all great things to do. Okay. The example that we looked at from last chapter was about drive theory of aggression, that if you can get out, that if you can use an outlet for aggression, then you won't be so aggressive in your relationships, etc. So according to the drive theory of aggression, if one group observes a violent hockey game and a second group observes a gymnastics competition, then the group watching the violent hockey game will behave more aggressively. Okay. So we found that the hypothesis is falsifiable and has actually been disconfirmed. Okay, that drive theory isn't really supported by evidence that has been tested. Another example of a falsifiable or of an unfalsifiable hypothesis that comes from recent events is the idea that there are microchips in vaccines. So there are people that believe that there are microchips in vaccines, that if you get a vaccine, then the government can watch what you're doing and everything and keep track of you as if we're that important or interesting, right? Most of us wouldn't care if somebody were watching what we were doing. It's boring. But anyways, There are people that think that there are microchips in the vaccine, the COVID vaccine, and what they will say is that, is there a microchip in the vaccine? And they will say that yes, there is a microchip in the vaccine, and then there's no way to really test it. You could look at all the vaccines, you could look at them under a microscope, but there are all these ways to wriggle out of the results. So even if scientists said, we didn't find any, then all the people who believe that there is a microchip would say is, oh, well, you didn't find it in that one, or of course, it's being tested, so they're not going to put it in that vaccine, or it's too small, or the technology is too good and you can't see it under a microscope. Whatever it is, they've made it unfalsifiable just because they won't accept the results, and there are lots of excuses of a lot of excuses for why the results didn't work out in their favor. Also, it's difficult to prove the non-existence of something. You could test all the vaccines on the planet and miss one, and then you're not so sure that one didn't have it. It's a little bit far-fetched to think that way, but it's still possible. So the nature of scientific testing of hypotheses is that the way that we test something needs to be falsifiable. We need to be able to come up with a conclusion that is either confirmatory or disconfirmatory without any reasonable explanations to the contrary. Okay, so the nice thing about falsifiability is that we can correct ourselves if something is disconfirmed. So if we have a hypothesis that says something like, people who study the night before an exam have better test scores than people who do not. So if you have this kind of hypothesis where you're testing two different groups of studies versus non-studiers, let's say that the people who did not study had a better test score on average than the people who did study. Now, that's interesting because we have we have a hypothesis that is falsifiable. We found our hypothesis to be rejected. The results weren't as expected. We ought not take that as this defeat. We ought to take it as, oh, there's something we just learned. We know something now. Something happened. People who didn't study did all right. So maybe we learned that the test was too easy. Maybe the people who studied the night before were up too late and they couldn't focus on the test when it was time to take the test. Whatever it was, we now learned something more. So falsifiability and failing to agree with the hypothesis is a good thing. We can learn from it. Right, so it allows us to look into ideas, to correct things, and to make different assumptions and assertions about the results. So falsifiability is a good thing in that way. Okay. When we do have a failed prediction, or our hypothesis isn't what we thought it was going to be, we have no need to excuse the results. We just say, oh, what we thought was going to happen didn't happen. And you will say why you think it didn't happen, but you don't make excuses for it. You can explain it, okay, but don't make excuses for it. You can say, oh, maybe this happened, or maybe this happened, or maybe this happened, but don't get defensive and say, oh, well, the result's not correct because ... No, the result's correct. Make an explanation for why it's incorrect, why you got it wrong. That's fine. But don't say that, oh, well, the results are not valid because, we didn't have a big enough sample, which actually could be relatively valid. But maybe like, well, gee, the people didn't answer honestly, or whatever it was. Don't just make excuses for it. If you do find through reviewing the data that, oh, well, people actually didn't understand the question correctly, okay, maybe you can make an explanation for that. But don't just say that it's wrong, you need to redo it because you didn't like the result. That's not how we do research. When we do research, and we do have these questions that we have, these questions that we can answer, that we can form hypotheses about, we have to come up with an organized way to answer those questions. And the way that we go about doing that is learning about research methods and designs. So lots of different examples of research methods and designs. Basic methods are qualitative and quantitative, and then the designs are kind of underneath those. So there is a very methodical way to answering these questions, and we'll talk more about this in a class research methods in design and also in stats. So we'll get more into that, but we do want to understand that we are kind of circling around this finer point about how we answer questions and how we go about conducting research. Now let's take a look at just those 3 criteria for showing causation real quick. So there are 3 criteria for showing causation in any kind of research design. And really the research designs that are susceptible to causation, there's really 2 big ones. A pure experiment, okay, so an experimental design, or a case study that's a time series design. Which means that you observe something time and time again. You introduce some kind of thing to change the behavior of whatever you're looking at. And then if that behavior changes, that's the first indication that there is covariation. Meaning that, let's say that somebody is a smoker and they smoke a pack a day. Okay, so that's 20 cigarettes per day. And let's say that they smoke 20 cigarettes a day for a year. Okay, so that's a long time. And if I use acupuncture on that person, let's say, you poke them in the ear with needles, I guess. I don't even know how that works. It really doesn't, I'm sure. But whatever. You have covariation if, after I poke them in the ear with a needle, acupuncture, they stop smoking altogether. Okay. Now, if eventually they start to smoke again, then you might say, oh, well, the acupuncture didn't work. Well, it did something, right? So it caused them to stop smoking for a little bit. And then let's say that they start smoking again, pack a day after a month. Let's say they start smoking pack a day again for another year. And I poke them in the ear again. Then they stop smoking immediately, and then they ramp back up. Well, what we can say is that there is covariation because when I poke them in the ear, they stop smoking. They do that time and time again. Let's say it goes on for 10 years. Okay. Now, what also has to happen is this thing called temporal precedence, meaning that the thing that I do needs to come before the thing that happens. So the cause needs to come before the effect. So if I have a smoker, they smoke a pack of cigarettes a day for a year, and then they stop smoking out of the blue, and then I poke them in the ear. Clearly, the poke in the ear is not what caused them to stop smoking. So that lacks temporal precedence. But because I poke them in the ear and then they stop smoking, we have what's called temporal precedence, meaning that temporally, in terms of timing, the cause came before it preceded the effect. Okay. Now, we also have to eliminate plausible alternative explanations. Okay, let's say that it just so happens that the week that I poke him in the ear, or the day that I poke him in the ear, he's going to his in-laws and they don't allow smoking, so he can't smoke at all. And all of a sudden, we don't have this cause and effect anymore because we thought that being poked in the ear is what was causing the lack of smoking, but really what it was the fact that he was going into the in-laws and wasn't allowed to smoke. And it just so happened to be that after we did this, year in, year out, we were timing it exactly with the time that he would go up to his in-laws for a trip every year. Okay, so that's a plausible alternative explanation. But if there weren't anything else that was a plausible alternative explanation, then in this example with using acupuncture for smoking cessation, we would have covariation, we'd have temporal precedence, and we would have eliminated the plausible alternative explanations. So it takes those 3 characteristics in order for us to demonstrate cause and effect between 2 variables. Now let's talk about the strengths and weaknesses of some research methods. And I'm going to kind of go over these a little bit shallower than what you might expect, but it's for 2 reasons. One, you don't really know about these research methods yet and haven't been able to practice them, so I don't want to get into too much detail. Plus, you will learn about them later. So let's take a look at some examples of the research methods and what the strengths and weaknesses might be. So a case study. A case study is a research design that provides some kind of description of, and it could be of a person's life like it says here, but it could also be of some kind of intervention. Like you could do a case study on somebody who has a particular medical diagnosis that's a rare diagnosis, so you want to use that one case and do kind of an in-depth exploration of that case and some interventions that you might provide. Or maybe it's a mental health disorder that's interesting and you want to talk about that. Or if it's of people who've experienced something relatively rare, like people who survive a plane crash or something like that, that could be some kind of a case study. But we really want to look at an in-depth aspect of a case and learn more about it and use a small sample size. By the way, we can also do what are called ethnographies. Where we are looking at different characteristics of people from different places. That would be considered a case too, because you're looking at a group as a whole as a single case. So it doesn't have to be just one person. It can be bigger than that. Okay. Some of these examples that you see there are when people would use interventions or cases with psychological problems that are relatively rare, like what Broca did with Tan. So strengths and weaknesses of a case study. Case studies provide a lot of good information, especially when things are rare or don't happen very often, or for people who have different specific knowledge or characteristics. So if somebody has some information that isn't shared widely, you can do a case study on that person or those people if you have a small group of them. You're treating them as one. The issue, though, with case studies is that the findings are unique and they're hard to generalize. So that means that whatever findings you have as a result of working with a particular case is reasonably specific to that case because of how specific the presentation was in the first place. This here says a case study cannot show cause and effect. There are some methods of deriving cause and effect in case studies. The one I gave earlier, using a time series design, is actually one of the exceptions to non-experimental designs that you can get cause and effect from. And it's usually because it's well controlled and you've developed a pattern over time. Now, naturalistic observations are interesting. So naturalistic observations, I like to call this kind of like people watching, where you watch some kind of event happen. I always talk about people. It could be with animals. It could be other things too. But we observe people in their natural field, and we don't attempt to intervene at all. We don't tend to let them know that we're watching them. We're just observing, which sounds a little bit cringy, right? But it's not as bad as it sounds. You know, it could be lots of different examples. You could be watching people at a cafeteria eating and just noting the number of times that somebody talks with their mouth open or whatever. You know, you could do something like that. It's usually not that big of a deal. The example that's given refers back to the Heaven's Gate study where Balkan Taylor, conducted a participant observer study where somebody infiltrated Heaven's Gate to study the members. A better example of participant observation, I think, more accessible to you maybe, is the Saw movies. So if you've seen the original Saw movie, I think it was like 2000, 2001 when that came out. Maybe a little bit later. Maybe I'm losing track of that. But the spoiler alert if you haven't seen it yet. The person who was responsible for the torture and things like that was actually in the room the whole time with the people that were stuck in there. So that would be participant observation. Kind of a weird thing, but you know, people get that example more than others. So some strengths and weaknesses. What's nice is that you can generalize the findings of a naturalistic observation to the general population because it's not a specific thing. You're not controlling anything. It can be said that people would behave in different settings just as naturally as the one that you're observing. Okay, that's all good. That works. The problem is that you can't control outside variables. Right, so if you're looking at sportsmanship during a soccer game, for example, and you want to note the amount of times that there is sportsmanship occurring in a soccer game, you could do that and it would be fine. But let's say it's raining and people are kind of wet and soggy and they're not, very happy about playing in the rain or whatever. You can't control for the rain or the weather or whatever it is, and that might affect sportsmanship. differentially, and that can become problematic when you're trying to generalize your findings. Okay, it cannot test treatment, so you can't implement some kind of intervention. The only way you could do that is if maybe you had some kind of participant observation going on and somebody was guiding what was happening. But then again, it's not as naturalistic as that point as if you had things just going naturally. Because if you put somebody in there to steer something, all of a sudden you take away the natural tendency of the people that you're observing to behave. So you have to watch out for testing treatment effects, and it cannot show cause and effect because there's way too much that you can't control for. It violates that last tenet where you have to control for extraneous variables. So survey research is interesting because it allows us to get a lot of information quickly, and it's kind of like a snapshot of people's opinions or attitudes, beliefs. We tend to use questionnaires, polls, surveys, whatever you need to get information. Surveys usually come in a couple different flavors. It's usually questionnaires where you ask people questions and then they answer, or interviews where you'll still ask them questions and answer, but questionnaires tend to be more like checklists and things like that, whereas interviews tend to be more open-ended. So you can ask people about survey items relatively quickly. Gallup poll is a popular one. So is the National Social Survey, where people will go door to door. Sometimes we call this the census. But the Gallup poll will ask questions about people about beliefs and parapsychological things that are kind of cool. Gallup is a company that has a lot of different areas that ask questions, and people can hire the Gallup company to administer different questionnaires and things like that. So the Gallup poll could ask people randomly, maybe through mail or email or whatever, about these parapsychological beliefs, and that would be a very reasonable questionnaire. So some strengths and weaknesses. Surveys are economical. You can get lots of information pretty quickly, so that's kind of nice. The problem is that it's about self-report. And people can answer questions however they want to. If somebody's in a bad mood, their answers are going to reflect that. So they're highly volatile to influences based on personality, based on temperament, and you can't really control how people are going to answer. Not that, let me back up. You don't want to control how people are going to answer, but you can't know what kind of mood somebody was in. So it's good for getting information about ideas and tendencies and things like that, but not about making assumptions about how people live their lives or what their dispositions are. Okay. There's also selection biases that occur. Lots of times people that want to take voluntary surveys are more amenable to them than not. So you might accidentally make conclusions about the results of the survey that are based on people who are willing to volunteer, who have resources to take time to do a volunteer survey, et cetera, et cetera. So there might be some kind of bias in the people that take it. Not because they have a bias themselves necessarily, but the way that you select people, the way that you find people might be biased. Okay. We also have correlational studies, which is kind of a specific method where you're asking about a correlation between numeric variables, like asking about things on a scale of 1 to 10, or the quantity of something, or the number of times somebody does something. So correlational studies are kind of specific. I don't want to really focus a lot on these right now. Because it is a very specific type of research design, and we'll talk about a little bit more in other classes. What I do want to talk about just a little bit, though, are these things called spurious correlations. Okay, so most people understand about what a correlation is, that as one thing goes up, so does another, like shoe size and height, or happiness and the amount of money that you have, which is maybe not true. But The spurious correlations are when people think that there is causation just because there is correlation. So let's take a look at a few of these to kind of give you an idea of how correlation studies can be misinterpreted. Here we are at a website, tylervigan.com, and this website has a bunch of interesting correlates between variables. And what's interesting about this is that these update automatically, so this is just accidental that it's a grim topic for the first one. Okay, this is a correlation between the average amount spent on science that the U.S. Does every year, and the number of hanging suicides. Now, these are scaled differently, right? So you see that the suicide scale is over here, and the spending on science is over here, but the intervals make sense. Just look at the graph for now. But you can see that there is a very strong correlation. We're not going to focus on the correlation coefficient, but it is 0.997, which means that 0.8 if you round it, 99.8% of the variation in this graph is caused by the relationship. Let me take that back. Is explained for by the relationship. I shouldn't have said caused by, but explained for by the relationship. Clearly, this is not causative, right? The number of hanging suicides is not causing U.S. spending on science and vice versa. So there's no cause there. This is just a spurious correlation where there are correlations between two variables that are really not related. Okay. This is a number of people who drowned by falling into a pool and how it correlates with films that Nicolas Cage appeared in. Okay, so on this scale we have Nicolas Cage films, and on this scale we have the number of drownings. So the red line is number of drownings, and look, there's this interesting correlation over time with drownings and the Nick Cage movies. Another interesting one. Per capita cheese consumption correlates with the number of people who died by getting tangled in their bed sheets. Can you imagine that? And it's interesting. There are more people per year that are dying by getting tangled in their bed sheets than people who are drowning in swimming pools. I have no idea why. But these are correlates. Last one we'll look at. Divorce rate in Maine correlates with per capita consumption of margarine. Okay, so it's very interesting that these correlate, right? But they're not being caused. There's no causation there. So you have to understand that even if we have a correlation, there is not causation there. There's a lot more that goes into causation than just having two variables that seem to go together. I can't stop looking at these now. Age of Miss America, and then murders by steam, hot vapors, and hot objects. Okay, very interesting. Who knows why these seem to go together? Really, there's no explanation for it. They just happen to be spurious. They just happen to correlate. Okay, I got to stop looking at these because they're interesting to me. Okay, click the button. We'll go away from it. Okay, there we go. Another thing that happens is that we can develop some kind of causation. We can develop some kind of causation based on observations and forgetting about one critical aspect of causation. We go back to a question that we started off with, I think in chapter 1, maybe 2, I forget. And the question was, do people behave more abnormally during a full moon? And if you look at this, you say, for people that have abnormal behavior during a full moon, there are 12 instances versus 6 instances. Okay, this is fictitious data, but it is kind of close to what reality is. It's just made more simple for the sake of teaching. So what we see here is that, wow, 12 people behaved abnormally during a full moon compared to only 6. That must mean that more people misbehave during a full moon than not a full moon. Well, kind of, but if you look at the relationship between full moon behavior for full moon people, for no abnormal behavior during a full moon it's 6, and then no full moon is 3. So actually the relationship between the people that did not have abnormal behavior on a full moon compared to a not full moon was the same trend as for people who did have abnormal behavior. So we have to always consider what the unobserved sample looks like. So we can't just say, oh, for abnormal behavior people, full moon to no full moon is a 2-to-1 ratio. Well, it's the same ratio for no abnormal behavior group between the full moon and the not full moon. So you have to look at the differences there, because what this indicates is that there is no difference between the people who are engaging in abnormal versus abnormal behavior between a full moon and a not full moon. And that's what the actual results suggest in research. Okay. This slide it further explains what happened in the prior slide with that cell letter C. Let me go back here. Cell letter C. And what happens in this example, this goes on to explain that we can disconfirm an association by looking at what's happening in cell C, because it says that there are people that are not engaging in abnormal behavior at the same rate during a full moon as there is for people who are not in a full moon. So if you look vertically, the ratio is the same between a full moon and a not full moon. There happens to be more people during a full moon in general who we sampled, but when we look at the ratios are the same, meaning that there isn't a significant increase in abnormal behavior in a full moon compared to a not full moon. But people forget to look at this cell in particular, but also people don't look at the no abnormal behavior group when they're trying to confirm that people behave differently during a full moon. So when we look at that uncalculated correlation, or we just look at the data in terms of the flat out numbers, we have to be aware of that. Okay, so with true experiments and causation, we've talked about how there are only a couple of ways that you can develop causation in terms of designing a method to study causation. So quasi-experiments. We start out with quasi-experiments because people kind of recognize what they are. And among experimental designs, they're the least reliable. And there's a reason why we call them quasi-experiments, because they appear to have an experimental design, but they're missing some kind of key aspect of a true experimental design. So a quasi-experiment looks at the differences between groups, but the difference between a quasi-experiment and a true experiment is that quasi-experiments lack control. Meaning, we're typically looking at differences between groups that already exist. For example, within reason, you can't randomly assign people to a male and female group. People already are parts of those groups, so we tend to use the groups as they are. So we lack random assignment in that way. That's kind of the big way that quasi-experiments differ from non-experiments. Not non-experiments. How quasi-experiments differ from experimental designs or true experiments. And that could also be like you can't randomly assign somebody to what school they attend or to what family they belong to. So you can't have a true experiment where you're looking at variables like that. It would be considered a quasi-experiment, and quasi-experiments have a certain set of strengths and weaknesses. So a quasi-experiment is good for comparing groups that allow some of the control over the extraneous variables, but not all. Because, if you're looking at the differences between men and women, there are certain experiences that women have different than what men have, so that those experiences become extraneous. Now, some research designs may not care about those differences, like they may not impact the overall research, but in some research it might, especially when you talk about attitudes and beliefs. Okay. They cannot show cause and effect because there is a lack of randomness. And because there's a lack of randomness, you can't really associate, or you can't create a cause and effect relationship, because something else might be explaining the differences between the groups. Now, a true experiment has some different qualities. It has an independent and a dependent variable, but what's different about a true experiment is that an independent variable, or what we sometimes call a grouping variable, can be manipulated. You can assign people to different groups within an experimental design. For example, we could see if a particular drug increased learning. Let's say that we have this miracle drug out there, it increases learning. We can assign people randomly to take a drug that has an active ingredient, or to assign them to a group that has a placebo, a drug that does not have an active ingredient. And in that way, we can manipulate the independent variable, the drug, whichever drug group they belong to, the treatment group or the placebo group. And then we would measure whatever we wanted to about learning, whether they could memorize something or whatever. And that would be the dependent variable. And we could control for other extraneous variables through random assignment or other control procedures. So let's say that we have 100 people in a group. If we randomly assign them one to each group, until we're done with all of our people, then we would probably do a good job of distributing all the random characteristics to each group. And even though the groups may not look exactly the same, we would have done an adequate job of randomly assigning whatever differences everybody has to each group. So each group, again, doesn't have to be exactly identical, but we do want to split apart those characteristics that might be tricky to control for between the two groups. So if we go back to that example where does study time affect learning, it helps us to define these two characteristics that we just talked about in the previous slide: independent variable, dependent variable, and control to a certain degree. So the independent variable is what the experimenter is trying to manipulate in order to affect the dependent variable. This is not any kind of naughty thing that we're trying to do. All we're trying to do in this case is say, okay, can we manipulate the amount of time that people study and see if there's a difference in how many words they can recall out of 50? Okay, so what we can do is we can say, okay, we'll give one group 10 minutes, one group 5 minutes. So we randomly assign everybody in this study 50 people. 25 of those people will study for 10 minutes, 25 will study for 5, and then we will measure them to see how many words they recall. And then we can see if there is a difference between those groups. So we will have manipulated the independent variable, which is whatever group they belong to in terms of how long they study, either 10 or 5 minute group. And then we will measure the dependent variable, and we can make a determination on which group had more recall words. And then we could say, as long as we had adequate control over our study, that there was a causal relationship between the amount of time that somebody studied and the number of words that they were able to recall. Now, if we wanted to incorporate the idea of covariation into this, what we could do is we would be able to maybe run the study again and have one group that studied for 5 minutes, one that studied for 10, and maybe one that only studied for 1 minute. And then we could see if there was covariation and see if we could get the same results over time. So we could see if we could get multiple people to engage in this study, and maybe we have 5 or 6 different trials and see if we get similar results. And if we don't, then that's good, because that means that we have a steady, consistent experiment. But we could also manipulate the amount of time that people study between these trials. Maybe we could have one trial where people study for 5 and 10 minutes, maybe where one group studies for 5 and then 15 minutes, and see if there continues to be a trend. If there is, then we can see if there is covariation of cause and effect. So we can see if the manipulated variables will differentially affect the outcome. In this case, can we change the amount of time that people study to affect the outcome of how many words that they recall? And if we can, then we have covariation. Now, this temporal precedence is a little bit easier to do in the example that we have, because we assume that people are going to study before they recall the words. And as long as the studying comes before the recall, we're in good shape. It'd be kind of silly to study afterwards, right? Then the last is, can we eliminate plausible alternative explanations? Well, if we can have a study where people come into a room, they all are in the same room and they are reasonably undergoing the same conditions, and the study doesn't take very long, and they're in and out quickly, then we can say that we've ruled out any kind of plausible alternative explanations. Now, we can't control what kind of mood they're in, right? We can't control what they experience that day and if it affects them or if they're sidetracked by something. But we can ask them about that. We could have them take a short 2-minute survey that says, are you experiencing anything today that's making you feel stressed out or unable to concentrate, we could ask them about other things related to the ability to engage in the experiment in an undistracted manner. And as long as they are reasonably undistracted, then we can say that we've ruled out distraction as a reason for their results. So we can eliminate those rather reasonably. Can we eliminate them all? No, but we can eliminate plausible alternative explanations that would lead to a difference in the way that they respond to the experiment. All right, so let's get into the last couple things here. We can wrap this up. We're going a little bit long this time, but there's a lot of information to cover. Let's talk about some thinking errors that lead to wrongly inferred causation. So we have this first one called the confirmation bias. Okay, so the confirmation bias is our tendency to only seek out information that supports the way that we already think, or to support the result that we're trying to get to. Confirmation bias looks different in different contexts, but if you're developing a survey, for example, where we want to ask people questions, you might accidentally word your questions in a way where people will answer a certain way. So if I ask a question like, wouldn't you like it if the food were better at the cafeteria? Okay, that clearly is a question that is leading. It's supposing that people don't like the food and that they would like it to be better. That's called a confirmation bias. We're trying to confirm a finding that people want to have better food in the way that you asked the question. Okay, so instead of asking that way, we could ask somebody simply, on a scale of 1 to 10, how much do you like the food at the cafeteria? Where 1 is I don't like it at all and 10 is I love it a lot. All right, so we could ask that question in a relatively unbiased way. There are lots of other ways that we could engage in the confirmation bias simply by ignoring other bits of information. We can ignore information about a research topic that does not confirm what we think. We could not ask questions on purpose because we might think that it would lead to some kind of alternative explanation for what our results are saying. So what we try to do is we try to come in with this unbiased approach to doing research. So in that way, we can look for disconfirmation. Okay, and that's okay. We can disconfirm, and that's okay. It allows us the opportunity to learn about something. And if we aim to disconfirm and we cannot disconfirm, then that is confirming in itself. Research is kind of backwards like that, where our goal is to kind of see if there is not a relationship. And if we can indicate that there is a relationship between two variables, for example, by showing that there isn't not, boy, what an inside-out sentence, by showing that there isn't not some kind of relationship, then we've done our job. Okay, so it's backwards. The way that we indicate causation or that we indicate association is by ruling out that there is not a relationship. When we get into research methods, we'll talk more about that as well when we talk about the null hypothesis. It'll get a lot clearer to you. Okay. Another thing that happens is that we confuse correlation with causation. Remember, things can correlate without them being causative. We looked at some spurious correlations. Those correlations are literally just correlations. Those two variables move together, but they are not causing each other. And there is no real relationship between them except for a statistical correlation relationship. Okay. Another thinking error that comes with this is the post hoc ergo propter hoc. That's a wonderful Latin phrase that means after this, therefore because of this, thinking that just because something happens after another, it was caused by it. We do this a lot in life. Okay, we look back and say, oh, well, those two things happened one after the other, so that means that the first one caused it. That's a lot of the time how we develop superstitions, is that we do something and something else works out for us, so we think, oh, I'll keep doing that thing, like wearing the same socks when you're on a hitting streak or something like that. We think that will lead us to have some kind of future success. But the reality is that there isn't a relationship between that. One of the better examples, I think, of superstition is when we're doing early studies on behaviorism, and you'd have pigeons that would peck a bar, and there would be this operant conditioning, and nothing would come out. Then the birds would get bored and walk around. I mean, they would do something like maybe go and peck at a corner or something like that, and then go back and peck at the bar again, and oh look, now there's food. Now all of a sudden the bird believes that, oh, if I go peck in the corner, I'll get another treat by pecking at the bar. And they do this, and they do it every time to get fed, even though it doesn't actually mean anything. So they're engaging in post hoc ergo propter hoc thinking as much as a pigeon can think. Now, they're not stupid, but they're still engaging in behavior. And what happens is that they believe this faulty relationship exists when it really doesn't. So be aware of these three thinking errors: the confirmation bias, confusing correlation and causation, and the post hoc thinking. Okay. Then last, we'll just wrap up with this. What is scientific thinking? Kind of circling back around to the original question. So what happens is that there is a problem. A problem exists when there's an obstacle between that initial state of not knowing how to solve a problem and the goal of solving it. So it's not about, do I solve a problem? It's how do I go about doing it? Remember, we have to have a hypothesis that that is testable, but what happens is that sometimes they don't know how to test it. So what that means is that you have to use critical thinking in order to go about figuring out how to test something, by asking the right questions, by finding the method, which is why we talk about this, because it's not enough just to have a question and wonder about it. Now we have to do something about it. Okay? So it takes creative thinking. It takes learning. We have to know these methods. We have to know the procedures to answering the questions. Creative thinking means that we have to be aware of other topics. We have to have a general understanding of the material that we're interested in studying. So we have to just know these things. That's why we talk about these things here in a very first class in critical thinking, is so that we can develop a mind for answering questions, for solving problems, right? So critical thinking in that way is problem solving. So when we think about, why are we talking about all these boring methodological things, it's because it's our responsibility to know how to answer a question, or at the very least to know when somebody is not answering a question appropriately, and to not be awed by some kind of thinking error that somebody is engaged in that they're trying to pass off as good scientific knowledge. All right, so that's it for chapter 4. I know it's a long chapter, and I know that this stuff can feel a little bit boring, but I promise it does become important as you go through your education and your careers, so that you can be a good consumer of research that can guide practice.